Welcome. In this video I'm going to show you how you can perform a Dunn test as a post-hoc test for the Cochran Q test. I'm using Python 3 and Jupyter Lab. So after this Cochran Q test you might want to know which ones are different. So we can perform a separate test for each possible pair, but then we have a small risk, usually of 5%, of making the wrong decision. So many authors therefore have different ways to solve this and counter for this with one or another way to adjust. So there are many different ways of doing that, but the most straightforward is probably Bonferroni, so that's the one I'll be using. The actual test itself for the pairwise comparison can be either McNemer test, which is equal to Cochran's Q test if you have a 2x2 table, or a Dunn test, and of course the focus of this video is on the Dunn test. This test was actually originally designed for after a Kruskal-Wallis test, and there appear to be two variations if you want to use it after a Cochran's Q test. The first simply transforms the data into a so-called long format and then does actually this exact same procedure as for a Kruskal-Wallis test. So that means it's probably using so-called ranks of the scores. So I'll call this the ranking method. Another one is an adaptation that's used by SPSS, another software program, and they actually use the counts rather than the ranks. So I'll adopt this the count method. I'll show both of them, which will make this video a little bit longer than usual. So let's dive in. The first thing I need is an example data. So for both of them, the same data file will be used. If you've never used a particular package, you can use exclamation sign pip install and then the name of the package. Usually that works. I've already installed the packages I need, so I don't need to install pandas, for example. I just now need to import it, and I'm going to abbreviate it with PD. Then I can use the read CSV file from pandas, so PD. PD, and then load the file from its particular location. Head will show me the first 5 records, and the only ones I'm actually interested in here are these last 4 columns. These are names of cinemas in Amsterdam. By the way, this is not real data, it's just fabricated data just for the example here. A 1 indicates that somebody did visit a particular cinema, and a 0 that he or she didn't. I'm actually only interested in in those last 4, so I'll move them into their own little selected data frame, and this will then indeed have only those 4. Now the ranking approach for the Dunn test is actually available in the scikit Post-Hocs package. So if I load that in, then we do require a nominal variable and a ordinal or scale variable. So we can do that now by transforming this to a so-called long format. And what that will do is actually put a munt in front of all the records here, and then put movies in that same column, and then copy all those scores underneath, and then copy all these scores underneath that, but then with Tushin, and then copy all of these. There are more, these were the only 5 underneath, and then as a label basically arena. So I can do that in one go with pandas by using melt. I'm going to use a variable name cinema and whether or not they visited has visited. So now, as you can see, I have loads of munts because it's actually going over these first, and then have another variable now cinema with munt, and then underneath all of those will be movies, and then all those scores, etc. And then I can simply use that function. I'll have to say that I want to use that Bonferroni adjustment method, and then I get a cross table. The diagonal I can ignore because that's a comparison between arena and arena, for example, and that doesn't make any sense. And you can actually also ignore anything above the diagonal or anything below, depending on what you prefer, because that will be the same. So if you look carefully, this one here is the same as this one here, because this is the comparison between arena and munt, and this is the comparison between munt and arena, and the result is of course the same. If we look closely, anything below 0.05 is usually considered significant, so these two seem to be significantly different from for each other. It's also possible to use a list with data. The data frame then needs to be converted into a list with a list for each field. Values to list can actually do that. So if I do list data, and then we can also use the Post-Hoc Dunn test and we get the same results. Then, however, these are not so clear, so we need to add the rows and column titles, and we can easily get those to get the same results as before, but now in a different order. In the appendix, I'll show how you can do this variation of the Post-Hoc Dunn test by going over the formulas, avoiding that package. Now the count approach is slightly different, and that's the one that SPSS uses. Here's some a link to some more info what they're doing there. And first, to do this one, we do need to go over the entire formula. So first, a few useful variables, constants. The variables themselves, I'm going to call the names I'm going to keep as variables. Then n is the number of cases that we actually have. I can pick any of the columns there because there shouldn't be any missing values. K is the number of variables that I have, and there were apparently 150 cases and 4 variables, as I already knew. Then I need the column total, so I can simply say sum, and that gives me that 81 people visited the Munt. Now the sum per row, so I can simply say here sum the rows, and then I can say axis equals 1. We also need the square of these row totals, so I can simply square them. So 3 squared gives me 9, for example. The standard error is then this scary looking formula, but we actually have everything in there that we need, so I can simply fill out all my results. For the Bonferroni adjustment, I need to multiply later the p-values with the number of tests that I perform, which can be done by using this little formula. In this case, we're going to do 6 different tests. And the test uses the normal distribution, so I also need the norm function from SciPy_stats. Now for each comparison, we're going to do the following. We're going to take Tij, I'm going to call this, which is the column of the total of the first variable and the other one, divided by the total n. And then we transform that to a z value by dividing it by SE. And the adjustment is then we can get a p-value from that z value, which is a normal distribution. And then the adjusted version will be that multiplied by that k, the capital K. So here's a bit of code that actually does all of that and stores it in a nice pandas data frame. And in the end, we then now get a slightly different format, but we get the comparison between which two cinemas, the test statistic that was used, the conversion to a z value, the unadjusted and the adjusted significance. Now, as promised in the appendix, I'll go over the ranking method, but then in the more difficult way. I'll leave a link to where you can find this Jupyter notebook on my website in the description below as well. So quickly to show you in the video, I have to use rankings, so I have a different ranking function for that. Then I can actually use the ranks. Once I have those, I go over this scary looking formula to correct for ties. That's being done in here. A small set of the categories, then store all the scores separately per category, rank all of those, determine each category the mean rank. I know this is going really fast, but that's why I said you can download the Jupyter notebook and read it on later. And then for each comparison we do all of this, and that's being done in this bunch of code. And then finally we have the same results as we had earlier. And just for verification, they're in a slightly different order, but you can see Munt and Arena, for example. Let me see, Munt Arena is here, 0.028948, 0.028948, so they're indeed the same. Alright, I do hope this video was helpful, and thank you for watching.